Hello everyone, Dr. Shane here, another Chemistry 105 video, and I apologize for the length of that previous one. That was almost 40 minutes. This one won't be nearly as long. Again, trying to be a little more efficient, getting down to what you just need to know before you come to lab, and then post-lab calculations. So in terms of what you need to be able to do when you come into lab, be ready for steps 1 through 3 as soon as you come in. It's basically just putting some water on a hot plate and boiling it. And then measuring something. So our goal today is this lab is called Calorimetry, or Calorimetry, depending on how fast you say it. Means from Latin measuring heat. Our overall goal is to determine a physical property of this, whoa, there it is, object. This is the same aluminum cylinder that you used before, so sorry for the disembodied hand here. And our ultimate goal is to calculate what's called the specific heat capacity, which is a physical property of aluminum, to calculate that using lab data and match it up to what the accepted value is. Kind of like we did for density, but this is using something else. It's a neat experiment, and let's go ahead and review the procedure. Then you can stop the video and then watch the calculations another time. All right, here we go. So this is the lab. Whoa, there it is. Make sure you have that printed out, ready to go before you come in. Okay, so let's kind of race through this. So steps 1, 2, and 3. Pour approximately 300 milliliters of tap water into a 400 milliliter beaker. I just grabbed a beaker out of the drawer here. This is not a 400 milliliter beaker. So get a 400 milliliter beaker and put some tap water in. It says about 300 milliliters, that's fine, but I'll show you what that means later. So you have that there. That's something I'll explain later. Record the mass of an aluminum cylinder and describe it, kind of like you did before. So make sure you get one of these. I'll probably have these laid out. Record its mass. You know how to do that. All the all the significant digits. Record what it looks like. Place the cylinder in a large test tube. Do this carefully so you don't smash it. Okay, that goes in there. And then place it in the boiling water. I think actually this goes fine. It's helpful here because you'll end up transferring this, and this may help. So it kind of, when you have to put this into this container at some point, it's helpful if you kind of have it ready to go. So it pours out of there quickly. Okay. The key thing is the beaker of boiling water. The water has to be above the level of the aluminum. If you don't put enough water in and only like half of it is submerged, the aluminum cylinder I mean, that won't work. So you want enough water, tap water is fine, because you're just heating it, it's not a chemical reaction. You want that in here. So you're gonna have this in here about 15 minutes, because what that does is that assumes that the temperature of the water, about 100 degrees, right, it's boiling, 100 degrees Celsius, about 212 Fahrenheit. We assume that that's going to be 100 degrees. Now, you're going to record that temperature, I think. Initial temperature of water, okay, I'm getting ahead of myself. So we have some thermometers over here on the side of the room. Grab a thermometer. You can use this. There's also a thermometer that comes in here, but you can use this one. And the temperature is reading about 19.0. You should get a decimal place precision on these thermometers. So 0.5, 0.2, 0.0. And eventually you'll measure the temperature. I want to point out how to measure temperature. What you don't do with temperature is drop the thermometer and let it sit. Because now what it's doing, it's touching the bottom, and it's probably too high of a temperature based on this hot plate. So you want it suspended, the bulb, suspended in the liquid, so that it's not touching the bottom of the sides, so it's only recording the temperature of the boiling water. I'll get to where we use that later. Okay, and that goes for 15 minutes. So do steps 1 through 3 as soon as you walk in the door. You're ready to go. If that's all the time you have for this video, stop it, and you can watch the rest of it later and figure out the rest, because you'll have time to figure this out. Okay, you can see I don't have many notes on the board, so that's steps 1 through 3. While the cylinder is heating, nest 2 foam coffee cups together. Well, we can do that. and taking 2 coffee cups and putting them together and putting water in is fine. We may actually end up using this. So it's a little bit more sophisticated, but styrofoam works well. Coffee cups, I don't think you need me to tell you what coffee cups look like. If we end up using this is called a calorimeter. It has a nice lid on it. Coffee cups, we don't have the ones with lids like you get at Dunkin' or at Starbucks. And this whole thing lifts out. And you can look at this. There's actually styrofoam in there. So it's a pretty good insulated container. And then we actually can do the experiment right in here. So this little container is pretty well insulated. So you can actually just use that by itself rather than 2 coffee cups. Or if we want to, we can put this lid on top. Just to be a little careful. This thing, see what I mean? It's plastic. Too much coffee this morning. This thermometer has a stopper on it, so it sits in there. Maybe it's good that I do this so I can show all the things that could go wrong. You don't have to worry about this. That's just, yeah, that'll just release into the atmosphere. You leave that on. And this is there just to stir the water and make sure it's homogenized. The temperature, when it goes up, goes quickly. So you can use this if you want to. You don't really need to. The thing you want to check when you put this back together is that the thermometer is not touching the bottom, that it's suspended. And if you have to, you can ask your instructor for help. Actually, I would ask your instructor for help. These can be difficult to adjust. So I think it should be fine the way it is. Okay, so we may use this instead of the coffee cup calorimeter. Okay, let's see, what does it say there? Step 5. Put 100 milliliters of water. It's kind of a long part of the procedure. Take 100 milliliters of water and put it into here. Okay, so measure 100, I don't need to tell you how to measure 100 milliliters. So 50 ml cylinder, twice it even tells you that. Now, you can use tap water at the ends of the benches. That's perfectly fine. I don't really need to provide that to you, but you want to get that in here quickly so it has a chance to equilibrate to room temperature. So this is going for 15 minutes. Get your water in here. In fact, what might be good is to get a beaker of water from the tap and let it sit out in room temperature so it has a chance to warm up the room temperature coming out of the tap. That's not a bad idea. Okay. Yeah, and then it says place the cups in a 250, like shove the cups in a beaker for more support. You don't necessarily have to do that. Okay, here's what I want to go through. Again, that is really all of the procedure. So you're going to do this procedure once with 100 milliliters of water in here, once with 85 milliliters of water in here, and once with 75 milliliters of water in here. If time is tight, we'll only do 2 trials. I'm going to talk about trial number 1 with 100 milliliters, take you through the procedure, but actually more importantly, go through the math. What are we doing here? The math is on the back, and it's all spelled out, but I want to go through this step by step and show it to you how this works and give you a little bit of a heads up. I'm not going to do any of the math. I'm just going to kind of outline it for you. Again, stop the video if this is all you have time for pre-lab. Now we're kind of going into pre-lab, post-lab mode. All right, let me get some space here. Again, the purpose of this lab, quantitatively, is to calculate what's called the specific heat capacity of aluminum. It's a measure of how much heat does it absorb, how much heat does it give off quickly. Okay. All right, so I'm going to kind of go back and forth here. So let's just briefly review the procedure. Record the temperature of the boiling water. If you really want to be precise, you'll use the same thermometer for everything, so that you can do that. So you record the temperature of the boiling water, which we're going to assume is the initial temperature of the aluminum. So the initial temperature of the aluminum should be about 100. We'll probably be a little less than 100 degrees because we are a little bit above sea level, 500 feet to be more precise about. Allow the thermometer to cool to room temperature, okay. Grasp the test tube with the holder and carefully slide, okay. Yeah. Oh yeah, you need the initial temperature of this water in here too. So the initial temperature of this is going to be about 100. The initial temperature of the water is going to be about 20 or so, 19. So initial temperature here, initial temperature here, make sure you have those two. You have to have those two. If you don't get those two, that's bad. So then what you do, this is a little tricky, is take that out. You want to get this piece of aluminum into this room temperature water as quickly as possible. As soon as you pull it out, it's starting to cool down. That's a big source of error, is not transferring it fast enough. Again, I'm not going to do all of this. So you've got your water, you've got your aluminum cylinder. We may adjust the volumes in here. It doesn't really matter too much. So then what you do is slide that in and more quickly than I'm doing, put the lid back on. And you want to see how high does the temperature go on this thermometer. It will not go up very much. It may only go up a degree or two with 100 milliliters. And again, we may adjust these volumes, because if we use 50 milliliters of water, the temperature is going to go up more than 100. Maybe that's intuitively obvious. So we will see. Okay, some sources of error. The aluminum is sitting on the bottom of this container. So some of the heat is not going into the water, it's going into the aluminum container. That's a source of error. Okay. So that was step 10. Stir the water using the thermometer or the little stir bar, if that's what we're using, or the little stirring device, until you reach the highest temperature observed. It's not going to go up very much. That is the final temperature. Excellent. Continue to boil the water. You don't need to record that every time. Once it's boiling, it should be the same temperature. And you do this twice again with 85 mils and 75 mils. That's the procedure. Pretty straightforward. The thing is, once you get this high temperature, get the aluminum piece back in here, get it back up for 15 more minutes. We may not have enough time for 3 trials if we do 15 minutes. We will see. And then now the rest of its calculations. Let's take a look. I just have a schematic diagram here. So this is trial 1. You should be able to do some of this. If you know the volume is 100 mils, and you know the density is 0.998, that's given right there, you should be able to calculate the mass of the water, because we're going to use the mass of the water in here. If it's 100 mils, and the density is about 0.998, well, guess what? It's going to be 99.8 grams. Okay, you can do that math. Just make sure you show that. That's actually step 2. I'm kind of going out of order. So then you'll have this piece of aluminum. So aluminum subscript S, and its initial temperature is going to be about 100 degrees Celsius. Well, make sure you write down all the sig figs. You should be able to get a decimal place on that. Well, then what you're doing is you're taking this aluminum and you're putting it in here. And then you're going to have some final temperature of these water and the aluminum combined. And it's not going to be very high. It may be, I don't know, 22 degrees, 23 degrees, 25 degrees. But it's probably going to be, I'm guessing here, probably less than or equal to, I'm just going to say, 25.0 degrees Celsius. I honestly don't know, but the temperature of this water is not going to go up very much. But the final temperature of the water and the aluminum are the same. That is an important piece. They both have different initial temperatures, but they have the same final temperature. That is a crucial piece of information. Okay, briefly. So your calculations, which are called results here. I'm not going to go through all of this in detail. It's all spelled out for you. So for each trial, calculate the following. Okay, so you're going to calculate the change in temperature of the water. And change is always final temperature minus initial temperature. So the final temperature is this, the initial temperature is this, right, for water. So you're going to get a pretty small answer here. It's going to be small. It's also going to be negative, isn't it? If the final temperature, well, no, that's not right. The final temperature is higher than the initial temperature, so no, it's going to be small, but that's going to be positive. And that's number one. Well, then for the aluminum cylinder, the change in temperature for the aluminum, it's the final temperature, which, by the way, is the same as that one. Those are the same. Minus the initial temperature of the aluminum. The initial temperature of aluminum is like 100. So this is going to be a pretty big number. And it's going to be not positive, negative. So make sure your two delta T's are, so the delta T of aluminum is big and negative, the delta T of the water is small and positive. I'm on the back side now. Use 0.998 as, okay, calculate the mass of the water in grams for each trial. You can do that. Okay. I'm actually going to combine steps 3 through 5. So steps 3 through 5 into 1. Nice. I don't know where you are in lecture. So I'm going to give you a brief lecture here. So you may have heard of the first law of thermodynamics. You can create energy. You can't create energy or destroy energy. You can simply transfer energy from one kind to another. Another way of saying that is energy is conserved. Okay. I'm not going to do a lot of theory here because Dr. McCann will do that. So what we're going to end up doing is we're going to calculate, assume that the heat given off by the aluminum is hot. It's giving off heat. That's exothermic. That's a good vocabulary word. So heat is being given off by the aluminum and it's being absorbed by the water. So we're going to assume that the heat given off by the aluminum is equal to the heat absorbed by the water. Excuse me. Fine, and we call that, we give that heat is given the symbol Q. So the heat given off by the aluminum is equal to the heat absorbed by the water. Your lab manual, or the lab sheet goes through this calculation a little bit more stepwise. And there are 3 variables that make up the heat. And I want to make sure that I'm setting this up exactly the same way as the notes. And actually, it doesn't really matter where it is. Because these two are opposites, the heat flows from one to the other, we actually put a negative sign somewhere. It doesn't matter if you put the negative sign here or the negative sign here, but guess what? Since this delta T for aluminum is going to be negative, I'm going to put the negative sign over here. Because you'll have a negative times a negative, and that'll give you a positive, and that takes away any confusion. And this is all spelled out. So there's 3 variables that go into the heat. So I'll keep that negative. It's the mass of the aluminum piece, and you know that number. You recorded that mass. That's the mass. Times this variable we're trying to calculate. S is called the specific heat capacity. This is what we're solving for. We're going to solve the equation for this. Times the change in temperature of the aluminum. Well, we already calculated that. So it's going to be negative times a negative. That'll be a positive. Equals all of that stuff for water. So the mass of the water, which you already calculated, the mass, so not the volume, the mass, times the specific heat capacity for water, which you are given a value for that, I think, I hope. Yeah. 4.184. And this has units that are really important. The units are, the unit of heat is in the numerator, and that unit is capital J, joules, named after James Prescott Joule, a physicist from England. So it's joules divided by grams times degrees Celsius. So that's a given. You use that there every single time. That's not measured. Times the change in temperature of the water. So you have numbers here. You've got a number for that. You now have a number for that. You have a number in units, excuse me. You have a number for that. You have a number for that, a constant. And you have a number for that. So you should be able to solve the equation. So put in all that data. Calculate this side. Bring these two numbers over there. I don't know if this is helpful to you. If I want to do this, so the specific heat capacity for aluminum is going to be the mass of the water times the specific heat capacity of water times the change in temperature of the water, all divided. So that's going to just be numbers. Number. Oh, and then check the units. Grams and degrees Celsius will cancel, leaving you with units of joules in the numerator. I don't know if that helps you. So it might just be simpler to put in numbers and calculate and solve for this. But if you solve it using symbols, you just take these two, divide each side of the equation by that, and bring those over here. I think I did that right. And then work out your units. You're going to have joules in the numerator, grams and Celsius in the denominator. So the units of your answer, so the units will actually be those. The same units, not the same number. And then go from there, and I think that's it. And then you'll do this calculation 3 times, maybe 2 if we don't have time, and you'll calculate an average, and that's all there is to it. Okay, folks, procedurally it's a lot simpler than 2 weeks ago, or last week, and whatever it is, I'm making these videos on the same day. And that's all we have for today. Good luck, and keep it up. Hopefully we're still on campus at this point.